Let's then continue exactly where we left off on Monday. And we talked a lot about memory as this physical and this logical, or sort of architectural view of where we are storing our ones and zeros for our program's purpose. And we started to talk about the different types in C. And I mentioned how C is a strongly typed language, and we don't really need to know what formally that means, but other than to know that as we create our variables in C, in kind of the first step from day one, and as part of that problem-solving process, we do have to think about what types our variables need to be. Other languages let us kind of postpone that decision or kind of hide that decision for us entirely. When you're in the C programming language, as we are this semester, we do have to think right away whether it's going to be an int, a char, or a float. There's a lot of different variants of those types. Sometimes the syntax can get a little wordy where even unsigned, long int. We do pretty well by just int for whole numbers, char for text data, or floats for fractional data. But I'd like to start off today with just a couple minutes with turning to your partner. You may have to move a little further to find your partner, or just make a little huddle of people around you, and discuss this concept for the following 6 types here, which is more than just the basic 3, but just some obvious kind of variants of the basic 3 types there. And I just want you to think about not an exact value it needs to have, but as you are working on any arbitrary program, to come up with some type of variable that would need to make use of each given type. Another way to think about that same exact question I want you to discuss with your partner right now is, for what circumstances would it make sense to have an int in a program? What could any variable that I may want to have be? Maybe some of the examples you've already done for your coding practice would be a good example of that. For what point would it make sense to have an unsigned int versus potentially a shorter int versus that char, and then the float and the double precision as well. So take just a couple of minutes and turn to your partner or find a partner nearby you, groups of 3 as well, and discuss this particular question. Because again, as part of your programming and problem solving process, we like to draw things out what we want to do always, but what are my variables? Not only what are they named, but what type are they going to be? You're going to have to be solving that question or answering a version of this question kind of over and over again. So this is synthetic because there's no program we're writing, but what would be a type of variable, and come up with 6 examples, and we'll briefly circle back and discuss. So let's take 2 minutes with that. With your partner, what do you guys discuss? Introduce yourself if you haven't already. Okay, let's circle back, because there's a point here to this exercise, and I'm hoping that we're not going to go in circles with my perspective on this point. But let's start with the integer. Any examples that you came up with, feel free to share, and don't all jump out at once.
Number of animals.
Absolutely, right? We had that in class the other day. I have how many dogs you have and how many cats you have as an integer. If we wanted to be really nitpicky, is an int a good choice for the number of dogs? If you say no, you can tell me no. Why?
Because you can't have a negative.
Yeah, what does it mean to necessarily have negative dogs, right? So I'm saying nitpicky, I'm not saying it's wrong at all. Nitpicky, what would potentially be a better choice for the number of dogs you own? Possibly unsigned. And again, this is nitpicky. The follow-up question I think is important. Is when in your program would it make a difference whether you've picked a regular old int for the number of dogs or an unsigned int for the number of dogs in your program? When would it make any difference to your program?
2 billion.
That's exactly the right answer. So that's exactly right. It only will have any influence on your program when you get over 2 to the 31 dogs in your program. And okay, with dogs and with any variable, you don't want to over-optimize, but you can also think of it in those terms. Okay, I'm going to go with int. It's kind of sort of the default for whole numbers. Will this come back and bite me, no pun intended, later on with my number of dogs? Probably not. But when it does happen, you have to track that down and figure out what will happen. We will talk about today and on Friday, what happens when you're not fitting within your data type. So that's a good point. Number of dogs, int is fine. Unsigned int is probably more correct, but there's a very small window of values for which your program will have any difference, and it's in that 2 billion to 4 billion range for your number of dogs. How about number of people, though? Well, it's hard to say, right? Number of people probably also doesn't go negative. It depends. Is it number of change in people, or is it just total number of people? If it's population of Iowa, unsigned, I gotta think about that. No, that would still wouldn't be big enough for Iowa. Population of Ames, Iowa, unsigned short int is probably okay for now. Int is probably okay for now. Population of the Earth, well, it's actually not okay, right? And neither is unsigned int. You need, 7, 8 billion, whatever the number is now. You need something longer than that. You need your long int to be able to store that. What about for car? Did anyone come up with any ideas for car? Or char?
Days?
Sure. Days as in days in the month or days of the week. It is 0 through 6 or 1 through 7, and that is appropriate to be able to store that. As I mentioned, car is for text data, and we'll talk about a little bit about how that gets represented. So if it's text data, it's already car. It can also be thought of as this really short integer. Now, you've made the quote-unquote correct choice for you're storing the day of the week as a short 8-bit integer. What if instead, in an alternative universe, you decided to just use a regular integer to store the day of the week? What's the difference between your two programs? Yeah, the amount of bits that you're using to store that particular value in one version of the program would be just 1 byte or 8-bit, and the other version of the program would be 32 bits or 4 bytes. You have used 3 more bytes to store that particular variable. Does that matter? Well, it depends. It doesn't matter until it does matter. I still am the err on the side of not over-optimizing your code for worrying about a byte here and a byte there. Sometimes this does start to become an issue. We won't see it as much this semester. How about the distinction between float and double, which we also won't see very much this semester, but in certain fields it is kind of a critical distinction. Float versus double. Somebody else. What did you come up with for those?
Is that one like the number of sig figs matters?
Yeah, I guess so, right? I don't really say exactly what's happening here, but you can kind of get a high-level feel of maybe what the difference would be between the two, right? This has got 32 bits to somehow store this fractional information. This has 64 bits to store also some fractional information. And you can see there's a pretty big order of magnitude difference between them. So in doing scientific computations, it may in fact matter quite a bit. If I'm studying, something that's the base unit is in nanometers or something of that nature, and I really need a very large number to get really good accuracy, I may need to have double precision. If I just need to have fractional values because I want to be able to store 3/4 in my program because it is a fractional value, the regular old float is probably good enough. That is a more advanced topic, I would think, in understanding what is the right amount of accuracy your program needs for fractional values. For our purposes, if it's a whole number int, if it can't easily be stored as a whole number, float is the way to go. And I mentioned this already, talked about the relationship between bits and bytes. So in our memory, it's 1s and 0s that are being stored. And when I'm referring to the 1s and 0s, that's what I mean when I refer to something as a bit. It is an individual 1 or a 0, that binary notation. each bit's value from a physical perspective is based on some sensed voltage value in those SRAM transistor cells or in whatever technology is being used. And it's a high or a low value, or a 0 or 1 or a 0 value. Logically, at least from the programmer's perspective, we have our variables and they're being stored as these 1s and 0s. We can group those bits together to represent more complex data, and we talked about this on Monday, is one of the takeaways that I think is just important to kind of keep in the back of your head. If you have I bits of storage of a variable, that's 2 to the I unique things that you can distinguish between them. Some other terminology you will see here and there. Byte as 8 bits is a very common term. You always have to be careful. Is this thing measured in megabytes or is it measured in megabits? We tend to measure throughput like in terms of a network, in terms of bits per second, and storage in terms of bytes, but that's just some historical convention. In terms of underlying architecture, as you learn more about how these things are stored, you'll also hear the term half word. We won't use that too much this semester, or double word to refer to a 32-bit value. Usually someone, if they refer to a nibble of data, they're probably in their 60s at this point, and that's okay, but that's a half byte. From the C programming interface, everything is effectively a number of bytes. So a number of 8-bit values combined together. So while technically, like mathematically, an integer is any whole number in that negative infinity to infinity range, in C, depending on the version of the integer we choose, we have a fixed number of bits and bytes to store that value in memory, and there's an incongruity there, right? Conceptually, I need any arbitrary whole number to represent my number of dogs, potentially. In practice, there's a limited range of dogs I can represent in this program. I think you just need to be aware of that, and that's sufficient, that it may in fact cause you some bugs as we see code doing things that doesn't seem quite right, because math is telling us the result is something, and our program is telling us the result is something else. There's a couple other things that can be helpful as you may want to focus more on the size of things, and that is another part of the standard, C standard, which is the size of operator. Kind of looks like a function call, but it's effectively a built-in operator in the language itself. That takes as an input not a variable, it takes in a type, which could be both these built-in types and as we later create our own custom types, and it returns the number of bytes in that particular type. And this is where I mentioned I had a couple asterisks, if you remember, that some of these things are of different sizes depending on what particular operating system and underlying architecture you're running on. But at least we have the answer for our system, which is this Replit software, all semester long. For this class, you'll get these results. This isn't a bad set of values just to kind of have, in the back of your mind written down somewhere, or you can always just run this code or some version of that for you. It takes as input, again, the number of bytes associated with the variable type, and we can print that out like we can print out any other decimal number here. So when we do size of cars, they're 8-bit value, and it'll always be 8-bit for our purposes, and so when we call the size of operator, we get a value of 1 back. It returns the number of bytes associated with that particular type. And the value that you see there, you have your short, returns 2, int returns 4, as does long, float, double. There's also a long double, which is a 16-byte value that this system supports. And then finally, there's another feature of the C standard that is being kind of highlighted here. I thought about switching to this entirely. This is the standard int header. It's part of the standard installation of a C programming environment. This defines a whole different set of kind of labels for your data types that are just a lot more explicit about the size of those particular data types. You will see some code bases that use those types exclusively, and then other code bases that never use them at all. And I think I had to kind of choose, do we go down that path or not go down that path? And I said not to go down that path. But they can be really helpful when you're in a scenario where you really need to be very conscious of the size of your individual types. I could open up that file, but you can maybe kind of guess what uint8t is doing. Just the name of a type that I haven't defined for you yet. Based on the name of it, can we guess? How big is it? Can we guess? Someone said 2. No. Well, we got the result. We know how big it is. It's 8 bits. One byte. What do you think the U stands for? You have a guess? Unsigned. So it is equivalent to having a variable of type unsigned car. And if we were to look at the implementation of uint8t, it would be something like pound define uint8t unsigned car is basically all the definition would be for it in our code. That can be pretty useful. And it has all the other types in it. If I want a signed 16-bit integer, what would I call it using this notation? Can you guess? Signed 16-bit integer. Yeah, it could be sint. I think it could just be int and then 16t would be a signed 16-bit integer. So maybe you could also see potentially the value of having that as your data types in C in that standard int package here. Because you don't have to remember anything. Hey, is this int 4 bytes or 2 bytes or 8 bytes? I can't keep track of it. You're just very explicit in your program, and also for portability reasons, this is always going to be 2 bytes. It's always going to be 16 bits. It's always going to be signed. We're not going down that path. By and large, we are using the built-in types, which is an equivalent for each of these. But I think it's important to know they exist. You'll be reading other people's code, other library code, and headers that are defined elsewhere that may be using that, and that's all it is. Just a more explicit way of declaring the same exact type of variables where you're being very explicit in terms of signed versus unsigned, and here's the number of bits associated with those variables. So looking back at memory, going back to our logical programmer's view of memory, it can be a little bit more mature than what it was even back on Monday when we were looking at the programmer's view here. So instead of an arbitrary collection of ones and zeros, it is still ultimately, but instead of an arbitrary collection of ones and zeros, memory can really be thought of as this array of bytes. At least from the C programmer's perspective, all of our types are of 1 byte or larger, or some multiple of 1 byte or 8-bit values here. So when we start to think about our addresses and the data available at those addresses, we can really start to think of it in those terms. That when we declare something as an int, our 4-byte value, that's going to correspond to 4 consecutive addresses in memory. And these would be byte addresses. So byte address 0, 1, 2, and 3. And a byte stored at each of those consecutive addresses that taken together represent one 4-byte or 32-bit value corresponding to that int. So if we then have a program that has an int a defined, a short b, and then a char c and d, ultimately the compiler in association with the runtime system is going to allocate, in this case, 8 bytes for your program. There's not a guarantee that they're in this particular order, and there's also not a guarantee that they're actually sequential in memory and directly next to each other, but in general, in practice, that's how it works out to be. So those 4 variables corresponding to those 8 bytes give us this kind of view of memory where we have 8 bytes, the first 4 representing this variable, the next 2 this variable, and then an individual byte for those particular variables. We have an operator that we saw that gives us the actual variable's address. You're using that for scanf. And on Monday I mentioned, we very rarely need to know actual address. We need to be able to access it via that operator. That's actually a pretty common thing we do in our programs. But to know that the address is this particular number is not something we typically need to do in the programs that we write, but we have that ability to do so. If we print out with our printf using %p, there's more than one way to do this, but with %p, that's print as a pointer, and we can pass it a variable's address, and our program will actually print out where in memory for your particular system that this program is running on, that variable a happens to be stored. I'll show it to you just to show it to you to kind of maybe convince you that these things are actually stored in memory somewhere, that's kind of the main takeaway. There really isn't that much more to take away from this example than that just as shown on the slide, we're declaring a few variables here, A, B, C, and D, and we have the variable address, which is provided using that ampersand operator, and we can actually print out the value of that. And address of A is at %p, that's our print as a pointer operator in our format string. We pass it that address of A, likewise we pass it for B. And this is a 64-bit system, I don't know if you can read that. They're at kind of 2 arbitrary addresses in memory. You may not be that used to reading that kind of format there. OX, you'll get good at this, trust me on this. OX refers to hexadecimal notation is what this is. So it's not base 10 anymore, it's base 16. OX7FF, and how many digits do we actually have there? 7FFC, 5267, 577A, that's 12 hex digits. some 36-bit addressing that we have in this particular system, it's somewhere pretty high in memory that this is located. And in fact, it doesn't matter all that much. We declared A and we declared B in our program, and I kind of visualized it as being A first, or int first, and B next to it in memory. If you look at what actually got printed out here, the compiler actually did it in backwards order. For whatever that's worth, it's not a requirement to do so, because A is located, if you look at the very last digit there, that's C, that's 12 in hex. And this one, the address of B, is at location A, and our most least significant digit, that's 10 in hex. A is actually earlier than B in memory here. I don't know, and I can't say for certain, I have not tried it, if I just switch them around, does that in fact change where A and where B is? And it actually did, right? So in this case now, A is before B at a different location. I don't know if I run it multiple times. It's getting put in a different location each time. That's your runtime system doing some address space layout optimization here. There's some security reasons why it would want to do that also from a functionality perspective. We will eventually get a pretty good feel for where things are placed because there are implications here. We'll learn eventually about scope of variables in which it does actually matter if I define the int A inside my function or outside of my function, because in fact, the scope is valid. This will still be valid code here. Where that A gets put actually is quite different. The limitations on where A gets put is actually quite different. But from now, I think it's sufficient just to say these things are placed in memory. It's kind of on a byte by byte basis. And if we ever need to, we can reference via a pointer using that ampersand operator. And if we wanted to do a quick kind of sanity check that it's actually being placed anywhere at all, we can print via that %p and get our pointer value printed back out. Any questions about that example? Okay. So that's variables. We will keep coming back to that. There's implications throughout, the whole semester, really. We have to have our variables for the purpose of doing some operation on them, right? Sure.
Why can't you just print out the value of the variable right away?
Would that be something different? Like the value of the variable is what are those ones and zeros for where A is stored in memory. If I printed out A itself and not ampersand A, I would print this out. This operation is printing out, well, effectively it's printing out zero, it's printing out the address of A. And if you want to read that ampersand A as address of A, that's a valid way to kind of read that in English. So again, moving on to why we have these variables is to do some sort of arithmetic or logical operation on them. I don't think it's that hard necessarily to pick up because it is pretty common across most programming languages in terms of how you do the basic mathematical operators, at least for basic arithmetic in C. We have to be a little careful due to the typing requirements that you have to be aware of. Is it an int versus a float? But at least to start with, you can make a lot of progress in your programs with those 5 operators. So you have the addition operator. Sum equals sum plus temp. Takes the value of sum, loads it from memory. Takes the value of temp, loads it from memory. Adds them together, writes the results back to memory at wherever sum itself was originally stored. So it overwrites, another way to say that, overwrites the value of sum with some, in this existing value, plus the temp value, whatever that is in our program. Same goes for subtraction, as well as for multiplication and division. And then a common operator that you see for integer arithmetic is the remainder. You also hear like modulo operator, it means the same thing. It's division and then taking the remainder when that division is done. So when I take 6 divided by 4, we'll get a certain value in our program. When I take 6 remainder 4 or 6 modulo 4, I'll get the remainder when that division happens, which would be 2 in this case. So 6 divided by 4 is 1 with a remainder of 2. It can be very useful for all sorts of purposes that tend to make really good programming questions to use the remainder operator to do that calculation here. So those, I think I just mentioned those are the 3 steps. So we have our evaluation assignment operator, and you have the things on the right-hand side. You do whatever arithmetic is specified on the right-hand side, and then that equal operator is what's storing the result back. We have to make sure we're ultimately getting the values that we want here for that operation. And this example I want to show because it's something that you will see early on closed it here. It's something you will see early on. Let me bring it back up real quick. Because as we're dealing with different types, we have to just be a little careful with what the operators mean for those different types. This one's called float math. And let's just walk through the code before I run it here to get a feel for what it's trying to do. So we talked about when we declare our variables, you don't have to initialize them at the time of declaration, but you can, and that's what's happening here. I'm declaring an integer called a, and at the time of declaration, I'm initializing it to a value of 5. Separately, I'm declaring two floats. One of them is called b, and one of them is called c, and I'm not initializing any of them at the time of declaration. I calculate b equals a divided by 2, and then there's a line here in which I'm taking c equals a divided by 2, but before doing so, I'm casting that value a as a float. We will learn a little bit more about typecasting, but they all kind of look like this, and this is the most common scenario in which you will do typecasting in C. By putting the type name in parentheses, I'm saying that whatever is next to that type name in parentheses, I'd like to treat the next variable or the next result as actually being of that type instead.
Why did you use a typecasting for B as well?
Because I wanted to show the difference between typecasting and not typecasting here, which is what we're going to show here. So this line 6 is b equals a divided by 2. C is treat a as a floating point value first, then take its value divided by 2, and then I'm going to print out the results. Any guesses what we'll see when we do this? You're allowed to guess. They're different. Somebody else. Yeah, it'll be, well, it's 5 divided by 2. It'll be, carry the 2.5, yeah. And then when we have it just as integers, what do we think will happen? It'll just be 2, right? And that's what we see. It'll just be take a, which is int, divide by 2, and store the result back as a float. Well, integer division is defined in C, but it's an integer divided by an integer. The end result is an integer. It is effectively just truncating that result. Not quite the same as rounding, but truncating that result because the integer itself doesn't have any way of storing any fractional information for it. So I wouldn't necessarily say with this example that B is wrong and C is correct. I don't think it's as clear as saying that. I think a more precise way of saying it would be if you really do need 5 divided by 2 with like that level of accuracy, you need to make sure you're dealing with floats throughout. So that, you may want 5 divided by 2 and get a result of 2, because maybe you just want to do integer division, but the results are different. I think that's the important takeaway there. There are other ways to kind of get the floating point result here. One is called like promotion to float, that if any operation actually is using a floating point value in the math itself, the whole thing is treated like it's a floating point value. So it was kind of subtle. What I changed on line 6 here was instead of a divided by 2, I did a divided by 2.0. Sometimes you'll also see 1.0 times a divided by 2. It's kind of the same concept. That's float promotion, and that's something that some people don't learn for several years after being a C programmer, but now you know it today. That'll also get the 2.5 result there. There's a float in the math. Everything is now a float. Typecasting is, I think, the more like human readable version of what we are doing here. Take a, which happens to not be a float, treat it as a float for the purposes of this math, and then finally do the division that we have here. Those are the different types that, as we're doing our assignments, we actually have to be aware of, that right away. And that floating to integer kind of conversion issue, again, this is a academic environment where I'm trying to give you questions where you'll kind of trip up on stuff like that. You'll see that starting, this week. You'll see that very soon here where you'll get a 5 divided by 2. And when you get the result of 2, think back to this slide where, oh, that's right. If I really want 2.5, I have to actually treat it as a float. There's also operator precedence. Does anyone remember PEMDAS or GEMDAS? This is actually kind of culturally biased. Not everyone learns it such a way. Did anyone learn like order of operations back in elementary school of when you have complex math, you group things in parentheses first, then if there's an exponent, you do that next, then you do multiply or division from left to right, then you do addition or subtraction from left to right. I have a 4th grader, so it's kind of fresh in my mind, but it's for whatever it's worth, and if you need to kind of refresh yourself on that, that concept is pretty well established in doing arithmetic. It's the same exact rules for C programming, at least, so that as you can take multiple operators and combine them together into more complex expressions, it follows that well-defined set of precedents in terms of the orders in which the operators are evaluated here. This is a very common thing to want to have in your code. We talked a little bit about this. It's never truly strictly necessary. I could have taken result equals total, and then temp equals count divided by. I could have done it on multiple lines of code, and it would have been equally valid code. But usually we have some arithmetic operator we're interested in doing, and if it kind of fits on our screen and we can see it, we tend to combine it into one line of code for our arithmetic operators here. But we just have to be a little careful. Just like when doing paper and pencil arithmetic, we have to be a little bit careful. And in this case, parentheses are a good way to remove any ambiguity. We don't deal with exponents as much, that those are separate function calls in C. But multiplier, division, or remainder, having precedence over addition or subtraction is something we do have to remember. In this case, count divided by max gets calculated first before we do total plus that value, and we take that value and subtract offset. So multiplication, or in this case division, happens first, then we go left to right with our additions and our subtractions. And I think it's okay. I mean, I think, again, you do it on pencil and paper, use your calculator, you should get effectively the same result when you do that in your program. If I really wanted total plus count divided by max, and this is arbitrary, maybe that is what I wanted, the easiest way to guarantee that is just to add some parentheses around it. I wanted total plus count done first, just put a left and right parenthesis around that, then divide by max. And it does exactly what you would hope in that instance. Just a quick sanity check then here. So for these examples, for the first one where we have A plus B plus C plus D plus E, that one is just left to right. So A plus B gets evaluated first, then plus C second, plus D third, plus E fourth. In that next example, A plus B times C minus D divided by E, what are the order of the operations happens here? What happens first? Absolutely. What happens second? That's right. So multiplication and division are kind of equal precedence from left to right. It's arithmetic, but it's a good reminder. And then B times C, D divided by E. What's next after that? The addition happens, and then the subtraction happens. So if this was 1, 2, 3, 4 for that first example, this example would be, I don't want to be wrong here, 3, 1, 4, 2, right? Because it's multiplication first, then division, then the addition, then the subtraction. We go left to right, but then there's that precedence here. How about that next example? What happens first? B plus C. Why? Because it's in those parentheses. Then what happens next? You can just say the operator, because there's only one of each. What's after that? Well, B plus C happens first, and maybe I missed if you said what happens second. But it's got the same precedence as division, so we would do all of our divisions, multiplications, remainder operators from left to right here. So it would be 1, then division, then that one on the right, the modulo, then finally that subtraction. And I would say for this example, if your code starts to look like this, like that example, it's not wrong. As long as you can understand it and explain why it's got those number of parentheses that you have, then it's totally correct. But if you start to have 8 or 9 grouped parentheses in the middle, maybe that's a sign you can break it down into a few more lines of code. There's no hard and fast rule there. But in this example, because of all those parentheses, which operator happens first? The most inner set of parentheses, so the subtraction happens first, then the addition, then the multiplication, because it's also within parentheses, so it's 4, 3, 2, 1 in this example here. We could spend more time on this topic. Like with any of these kind of just rules I'm introducing about C programming, it's okay to memorize them, you don't have to. It's okay to write it down, you don't have to. You just gotta try it, Okay, if I'm not sure about does the multiplication happen before the remainder or not in that example, well, just try it and print it out and you'll get your answer pretty quickly. You don't have to sit there wondering, staring off into the night, whether that operation happens or not. Try them both, see what happens. You can get your answer for those kind of micro questions pretty quickly here. As we start to reason about the programs that we are writing, and we'll build upon this over time, it is very nice to be able to kind of represent the relationship between our data and the operations that's happening on that data, and then the control flow that eventually will be happening on our data. And one such way to do that is to represent an expression using what's known as an expression tree, where the operators that are higher up, like physically higher in the tree, actually have that higher precedence. In other environments, it's arguably more important to actually draw those things out. I think as C programmers in this replit environment, again, as I mentioned, if you're unsure of the precedence, you can draw it out. You can also just try a couple different things until you get the result that seems correct for your purposes. I want to do this debugging exercise, but I don't know if we're going to have enough time to do it correctly. So let me bring up another topic first. I do want to do this exercise. It'll make a lot of sense on Friday. So let me zoom past that, but remind me on Friday, hey, you never showed us the GNU plot example, so let's not do that yet. Let's talk about characters and strings here. That this character type is more than just a small integer, although it is also just a small integer. It's also encoding the actual text characters. And the syntax for here is something you just have to kind of get used to through experience. If you have a single character literal, which means a constant of value, like for numbers it was 42 was a value, or 5 we initialized an integer literal. For our character literals in C, it's single quotes. So car, my car equals J. If it's a single character we've initialized something to, it goes in single quotes. But those car types are also small integers, so you can also initialize them via integers. So that other example here is also valid C. Just depends on what you want to use that data type for. We can combine multiple character literals back to back, and that's what I'm referring to when I call something a string. String has a couple more implications to it than just an array of characters, but for now that's a sufficient definition. If you have multiple of those things kind of back to back, that's when I've used the term already, a string. I called it a format string or a string literal. With printf or with other functions that use these strings, these multiple characters back to back, when it's more than one, then you have your double quotes. Why is it that way? I don't know. It just is. For historical reasons, and it's not changing anytime soon. Hopefully the compiler will tell you if you use the wrong one. But if it's multiple characters, hello, my name is Joe, double quotes. If it's just the letter J, single quote when we do so. But I think what's pretty important, and I don't know if we treat the topic well enough in this next slide here, this is just a random image grabbed from the internet. So we probably could have done a better job here. Lookuptables.com. Where else do you look up tables online other than lookuptables.com? There's this concept called the ASCII table. Don't think I've used the term yet. I don't even entirely remember what ASCII stands for. It is the standard, it's fine. It's American something something standard for encoding textual data using these 8-bit values here. This table, while you certainly don't have to memorize it at all, is actually kind of important. If I was in this class, taking the class, doing the labs, I'd probably print out that table and just have that in my folder, and just so I don't have to go online and find it every so often. I still have to go look it up and go to lookuptables.com or whatnot and look up the ASCII table. This is the encoding and the somewhat standardized encoding for these 8-bit character values and what letters they would potentially, and alphanumeric values they would potentially correspond to. So capital letter A is 65 in ASCII. And the multiple columns here are just the different representations. So 65 in decimal. So if I have in my program, if I have it here, this program is actually empty. Let's try it here. I have a character, we can keep calling it my character. And we know we can initialize it via just that character literal. And I can print it out. My car is, I mentioned this, is %C to print out an individual character. This code will print out my car is A, totally valid. But with that ASCII table in mind, you can actually do all sorts of basic arithmetic and get the results that maybe make some sense for you. A, and I'm just telling you, just to have it printed out, you do not have to memorize this ever, is 65. This would have been equally valid initialization for it. I also get my car is A. Likewise, even when I was going to have it as a string literal, because it is a small decimal value, it is a small integer, I can also do this. What will this print out? My car is what? 65. And so all of the rules of working with arithmetic, doing integer math and things of that nature apply to characters because they're all just effectively entries in this big table here. You have to be a little careful for that reason. Not all of these things actually are printable. But for example, it's not that easy to read here. It's here somewhere. When I want to print out new line, you can't really tell based on this version. Maybe there's a better version than lookuptable.com. When I wanted to print out a new line in my code, what did we add? We added this %n. That is, in fact, an entry in the ASCII table, and it's entry number 10 in your ASCII table. And you can always do it this way, but if, for example, I wanted to do it because I'm weird and just literally print out the character for 10, I'll get the same exact result back out. That you probably never would want to do directly, but just to show that there's a direct relationship between the entries in this table, that first column. Number 10 is, and I don't know, learning how to read this maybe takes some time, is new line feed, new line, that's pressing the enter button on your keyboard. Sometimes you want a tab, that's 9, that's a horizontal tab where you get a few spaces. The main ones we normally would want to be printing out would be these ones, starting around entry 48 for numeric values, starting at 65 for alphabetical values, starting at 97 for lowercase alphabetic values there. And that allows us to do some interesting kind of math, potentially interesting kind of math. If I have letter J, and we can print out my character as J, if I wanted to print out J, or my letter, is the nth, and %d just means decimal, nth is just me writing the word nth, just say nth, or whatever, so it would just be the dth letter in the alphabet. How would we do that? We got our ASCII table here. We know that J is 74. Capital J is 74. Yeah, absolutely. Whoever had that, way to go. That's awesome. Now, I would argue that that's a little hard to read, but I think it's correct. And if we're off by 1, it's okay. We try it and we check again. I have to actually give it my car here. Thank you. My car, and then my car minus 64. J is is it? I don't know. Is J the 10th letter of the alphabet? It might be the 9th. I don't know. Is it the 10th? Okay, excellent. Thank you. That is actually correct. Now, again, 64 seems like kind of a magic variable here, and it kind of is. But we can also figure that out by, it's really just that character minus A, which sounds weird. What does it mean to be subtracting A? A is just a way to represent the number 65. And so we're offsetting by A in that ASCII table, and then we're subtracting 1 back off from there. And so I guess a better way to check that code would be to check Z, which is the 26th, check A, which is the first letter of the alphabet. That's my testing methodology. If it works for A and it works for Z, it probably works for B through Y, but maybe check a few others as well. We will come back to this as well on Friday. For now, just recognizing that they're both short integers and their entries corresponding to this table will really help you when it comes time to kind of manipulate text in your programs, which we actually do a lot of in our programming assignments for this semester. Let's leave things here for right now, and we'll pick up right here on Friday with a couple more in-class programming examples.